Welcome to day 20 of the 2023 Advent of Code. For today's problem, we have some sort of a circuit system, basically. We have a bunch of machines connected by cables and they communicate through communication modules. The modules communicate by sending pulses, which are either high or low pulses. When it sends a pulse, it sends it to each module in its destination list. So basically, we have a directed graph. Each time a node receives a pulse, it might send out a pulse to everything that extends off of it. So there are a bunch of different types of modules. We have flip-flop modules marked by the prefix %, and they store a binary value. They start off, and when they receive a high pulse, it ignores it, but if they receive a low pulse, it flips, and then it sends out a pulse based on what it was. If it was off, it sends a high pulse. If it was on, it sends a low pulse. So you can also think of it, if it turns on, it sends a high pulse, and when it turns off, it sends a low pulse. Then we have conjunction modules marked by the ampersand, and they remember the type, so the high or low, of the most recent pulse received from each input to it. Initially, they default to everything as being low, and when they receive a pulse, they update their memory and then send out a pulse. If all of its inputs last sent a high pulse, it will send out a low pulse, and otherwise it will send out a high pulse. Then finally, there is a single broadcast module which will be named broadcaster, and it'll just forward the pulse that it receives. There is a module with a single button called the button module, and when you push it, it sends a low pulse to the broadcaster. So basically, it sends a low pulse out to everything that's connected to the broadcaster. After pushing the button, you have to wait for all the pulses to be done first before you push the button again. And the pulses are always sent in order, so if a pulse is sent to A, B, and C, then if A sends out a pulse, the pulse that was sent to B will be handled before the pulse that A just sent out. So basically, we store our pulses in a queue. And so for our puzzle input, we will get a configuration of all of the modules. And so our real input is not too long, but still a bit longer than the test, of course. And so in this case, we see that we have the broadcaster pointing to modules A, B, and C. Each of those are flip-flops. A points to B, B points to C points to I and V, and I and V is a conjunction module that points back to A. And so in this configuration, if we push the button once, it sends a low pulse to the broadcaster, which broadcasts it to A, B, and C. And so first, this pulse is processed. A receives a low pulse, so it toggles itself from off to on and sends a high pulse to B. Now before this pulse is processed, the pulse that was sent from the broadcaster is processed next, so B also toggles from low to high, from off to on, and sends a high pulse to C. Again, the broadcaster pulse is processed first, and so C also flips and sends a high pulse to I and V. Now this pulse is handled, but it's ignored because a high pulse sent to a flip-flop does nothing. Same with this. And finally, this pulse is handled, and a high pulse is sent to I and V. I and V only has one input, which is C. So when C is turned on, I and V now has all inputs high, and so it'll send a low pulse to A. This toggles A back from on to off, which causes it to send a pulse to B, which causes it to send a pulse to C, which causes it to send a low pulse to I and V. Finally, I and V now receives a low pulse, so its inputs aren't all high, and therefore it sends a high pulse out to A, which is ignored, and the cycle stops. There are no more pulses being handled. After this sequence, all of the flip-flop modules are off, so pushing the button again will do the exact same thing. And so here are some more examples. And finally, we want to know, after pressing the button 1,000 times, how many pulses are sent as a result, including the pulse sent by the button? So we want to take the number of low pulses and the number of high pulses, and we want to get the product of those two values. So let's use the second example since it's a bit more interesting. And so we should expect a value of this. Okay, so we need to keep track of a couple of things. We'll need to keep track of our modules, which we'll store as a dictionary from their name, and each module will contain the following properties. Its type, which will represent as just the character, its internal memory, and its outputs. So actually, let's make a class for this module. So this problem is a bit complex, so let's spend a bit more time making our code a bit better organized. So we'll have a module class, which will accept a type as a character and a set of outputs. Let's give it a name as well. So we'll store all these values. So we'll store its name, its type, and its outputs. And then we'll initialize its memory. So if the type is equal to %, we will say self.memory equals, we just need to store whether it's currently on or off. So we start them all as off. Otherwise, if it's a ampersand, then we start off the memory as a dictionary, which will store what the last observed pulse type was for each of its inputs, and we'll populate this data later. So now we can say modules equals a dictionary pointing from the name to the list of modules. So we also want a list of broadcast targets, which will be a list of strings. Now for each line in the input, we're going to split it on the arrow. So left, right equals line dot split the arrow. Oh, we also want to strip off the new line at the end. And so now we will get the left side, which represents the name of our module, and the right side representing the names of all of the outputs. So if the left side is broadcaster, we will handle this a different way. We will add right.split, comma, we will set that to the broadcast targets. Otherwise, we will say type is equal to the first character of left, and name is equal to everything else. And now we can say modules name equals new module with the given name, the given type, and outputs equal to right.split, comma. Let's put this here. So outputs equals right.split, comma. And so if left is the name broadcaster, we set our broadcast targets. Otherwise, we create a new module. Let's also define a representation function to get a nicely represented format. So we can say return self.name. I don't know how this is done. Let's just do this. So return self.name and then curly brackets, which will store the data. And then we can say type equals type, outputs equals, and then we can say self.outputs comma dot join self.outputs. And then we can also say memory equals, and then we can just stringify the memory. Okay. And so now if we print out broadcast targets, we see that this example only broadcasts to A. And if we print out the modules, we get this. So A is that is not even slightly correct. Self.type. Okay, so A is a flip-flop module, which outputs to inv and con, and its memory starts out as off. Inv is a conjunction module that outputs to B, and its memory starts off as empty. And finally, B is a flip-flop module that outputs to con. And finally, con is a conjunction that outputs to the output module. And so note that not all of the modules are one of the flip-flop or conjunction modules, so we do need to keep that in mind. Now let's populate the memory for each of the conjunction modules to store its inputs. So we can say for name outputs in, name module in modules dot values items. We can say for output in module dot outputs. So this gives us basically a map of all of the input-output relationships. We say if output in modules and the module of that output is a conjunctor, we need to add it to its memory. So modules output dot memory of name equals, and everything starts out as low. So now if we print out modules, we have all of our data populated. INV begins remembering that it receives input from A and it started as low, and con stores memory and it remembers that it inputs from both A and B and initially receives low for both. So now we're ready to start implementing the logic. So each time we send a button, so for blank in range 1000, we're going to keep track of the number of low pulses and the number of high pulses. Both start as 0. So each time we loop, we'll press the button once. This sends a low signal from the button to the broadcaster, so we can just do that. And now we want to keep a queue of our pulses because they're handled in order. So we'll begin with the queue equal to a dec, and we'll send a low pulse to everything in the broadcast targets. So we'll store this queue in the following format. We'll have it as origin, target, and pulse. The origin for each X in broadcast targets is initially broadcaster. The target is X and the pulse is low. Now we can say while Q is not empty, origin target pulse equals Q.pop left. And now we first say if pulse is low, then we increase the number of low pulses, otherwise we increase the number of high pulses. This could also be stored in a dictionary, but I don't think it really saves us all that much time. So first we keep count of the number of pulses we've seen of each type, and now we process it. So if the target is not in the list of modules that we know of, we can just continue. So for example, in this instance, the output module, we would just ignore it because it won't send any pulses out. So now module is equal to module's target. And so we want to see if the module type is a %, we will do two things. We begin by first flipping the module's memory. So module.memory equals on if it was previously off and otherwise off. And now we need to send out a pulse to all of its outputs. So for X in module.outputs, we will send a pulse by appending to the queue that starts from module.name, goes to X, and the pulse type is whatever the new value is. So we can say outgoing equals high if module memory is now on, otherwise low. Also, this only happens if the pulse is low. If the pulse is high, then we just do nothing. Otherwise, if the module type is a conjunction, we need to first update the memory. So module.memory of the input being origin is equal to the pulse type. And now we check. If all of it's high, then we send out a low pulse. And if all of them are, and if not all of them are high, we send out a high pulse. So outgoing is equal to low if all X is high for X in module.memory.values. So if all of the values of the memory dict are high, that means that all of the inputs, or all of the last inputs to this conjunction were high. So we send out a low pulse, otherwise we send out a high pulse. And now we can say for X in module.outputs, q.append module.name X outgoing. I have extra brackets here. Okay. And so now at the end, I believe we can just print out low times high. And that gives us our answer to part 1. So a relatively straightforward implementation. It is a bit long, but it's overall pretty straightforward. We just do as the task specifies. Now part 2 is where things start to get a bit shady. First of all, there's no test input, unfortunate. The final machine responsible for moving the sand is named Rx. The machine turns on when a single low pulse is sent to Rx. What is the fewest number of button presses required to deliver a single low pulse? So it's fairly evident that it won't be as simple as just run a loop. We have the advantage here of knowing what the output is already, but it's fairly evident that on day 20, the answer would not be so simple. And so for this problem, we have no given test data, so we can just discard the testing and only go off the real input. So I am not aware of a generalized solution to this problem, and we're once again going to have to rely on assumptions that are not given, just like in day 8. If this breaks on any of your inputs, please let me know and I'll create an update video. And if any of you have any ideas for a generalized solution that can solve this problem quickly enough, please do let me know because I would be very interested. But for this problem, we're just going to rely on assumptions again. So first of all, only one module feeds into Rx, and it is a conjunction module. The conjunction module in my case is named VD, but this might not be the case for everyone. Let's implement things as we go along. So we're going to first remove the low and high value. We no longer care about these. Okay. And now we'll need a couple of things. So first we need to know which module feeds into Rx. So we'll call it feed. I'll explain the syntax in a bit, but basically we need to say name for name module in modules.items if module.outputs if Rx is in module.outputs. What this does is it takes each module and it finds all the names for which Rx is in the output. And we're asserting here that there is exactly one. So we unpack it and assign it. Basically what this means is this is a tuple of length 1. It would be the same as doing this. And so it basically just means take the first element and assign it to feed. And this also asserts that there's only one item. So the problem with doing like feed equals just getting the 0th element is that it would work properly even if we find 2. By doing it this way, we assert that there must be exactly one item. If there are 2, we'll get an unpacking error. Value error, too many values to unpack, because we unpack 2 items but expected to find 1. So although we're going to make a bunch of assumptions, we're still going to double check that each of them are true. So now we know what feeds into Rx. And now we see what feeds into VD. So we have a couple of conjunction modules, 4 to be precise. And so we know that VD is a conjunction module, which means that it will output a low pulse to Rx if and only if the last input it received from all of its input modules was a high pulse. So I present the assumption that each of the modules that feeds into VD will produce a low pulse every single button press, except for on a regular interval, they will produce a high pulse instead. And what this means is that the first time that VD produces a low pulse is when all 4 of their cycles line up. In other words, at the lowest common multiple, so LCM, of all of their cycle lengths. Essentially what I mean by that is, let's suppose we have 2 inputs feeding into VD. One of them outputs a high every 5 cycles and a low otherwise. The other one outputs, let's say, outputs high every 7 cycles and outputs low every other button press. Then on the 35th cycle, both of them would output high. And so I have no basis for this assumption, and I don't know if this is true for every input, but I believe this has to be the intended solution. Because once again, it's just too convenient to possibly be a coincidence. It's probably engineered this way. So we're going to get a dictionary of cycle lengths, which will contain each name for which the module outputs to the feed, the module that feeds into Rx. So if we print cycle lengths here, also this is supposed to be name points to none. We start by storing the cycle lengths of each of the inputs into VD. We're also going to store a scene counter, and you'll see what this is for later. And actually, we're going to clear this and just make it empty for now. So now what we're going to do is each time we see one of these modules, we'll say if module.outputs. If feed is in module.outputs and the pulse type is if the module name is equal to VD and the pulse is high, then we want to record the cycling basically. So instead of a for loop, we'll now do while true, and we'll keep track of the number of presses so far. So when we receive a high pulse to VD, we will do two things. First, we will update scene. So the number of times we've seen the origin goes up by 1, and then we insert the cycle length if it's absent. So if the origin is currently not in the cycle length, then we'll say cycle lengths of origin equals the number of presses so far. So we're assuming that the first time we see origin output high to VD, that is also every n steps we will also get another high. And so we can assert that if origin is already in cycle lengths, that means that we know what to expect. And so if it has a cycle length of, let's say, 7, then we expect on the third instance it should be on cycle 21. So we should expect that the number of presses so far is equal to the number of times we've seen it times the number of the cycle length of the valley. And so we run it, it'll just hang, and this is a good sign because it means that this assertion has not failed. So also we want to make sure that it's not just stuck in an infinite loop somewhere. So we'll say if we've seen everything more than 100 times, if all x is greater than 100 for x in scene.values. So if the number of times we've seen each input to VD, sorry, this is not meant to be hard-coded VD. If the number of times we've seen each input go high is greater than 100 for everything, then we can be pretty confident that we're done. So we will say exit 0. So if we run this for a bit, actually 100 might be too high. Let's go with 10. So this exits, which means that we asserted that the first 11 times we saw each of the inputs to our feed value, in my case VD, it always followed this cycling pattern. And so now we can just say if all scene.values. So we've completed our assertion, which we're not going to keep in the actual program because it slows down runtime. This is what we get, cycle lengths, not scene. So these are the cycle lengths of all of the inputs. And now what we'll do is we'll get the LCM of all of them. So there is a math.lcm function, but it's only available in later versions of Python. I don't have it in my version, so I'll be implementing it using GCD. But normally you would be able to just say x equals 1 for cycle length in cycle lengths.values, x equals math.lcm of itself with the cycle length. So normally this would work. However, I don't have LCM in my math module, so instead I'll just do it the old-fashioned way of multiplying the values together and then dividing by the GCD. This does the same thing, but LCM is just a bit shorter if you have it available. And so that will give us the answer to part 2. So the key points for part 2 are we have to inspect the input itself. We observe that Rx is only fed into by one conjunction, and that conjunction is fed into by 4 modules that only feed into it. And so we need all of those to be high. And so we speculate that all of them will return low every round except high at a regular interval. And then we just need to grab the interval duration and take the LCM to extrapolate how long it will be until we see all of them high in the same press. I don't really like these problems because I don't like making these sorts of assumptions, and especially when I'm making these videos, I can never be sure if I'm giving out solutions that straight up don't work for other people. But unfortunately, that's just the nature of some AOC problems. There is no like correct algorithm to any problem in the AOC. It's just if you can get it right for your inputs, you've solved your problem basically. So please do let me know if you have a better and more generalized solution, or if this solution doesn't work on your inputs. But otherwise, that's all for today's video. Thank you for watching, and I hope you enjoyed.